Great, thank you. Well, thank you for the invitation. Thank you to Professor Buffon for the invitation to come today and talk to you about this project. This is a project that we're very excited about at Berkeley. It's something that we've actually been working on for quite a few years. And as you'll see, we think that there's real potential to do something on a fairly large scale around the globe with this project. But we're only going to be able to do that if we can build the collaborations we need with our colleagues in seismology around the globe. And you'll see what I mean by that, hopefully, as I go through the course of this presentation. So I'm going to be talking about MyShake, Global Earthquake Detection, Study, and Early Warning with Smartphones. And while there's a big focus here on earthquake early warning, that's not the primary objective. The primary objective is to collect seismic data to support all kinds of seismologic research. So I'm at UC Berkeley. At Berkeley, we run a seismic network, a traditional seismic network of instruments. And the challenge is always, how do you collect more data? How do you get the necessary funding to put these seismic instruments out to collect data that drives all of the research that we do? And that challenge is what led to the MyShake project. And the project is really very simple. I bet every single person in this room has one of these, either on the desk or in their pocket. And in every single one of these is an accelerometer that can record earthquake ground motions. And so if I can harness all of your smartphones to collect the data from earthquakes and share that data for research, we have the potential to build a huge seismic network to facilitate all kinds of studies. And so that's what we're trying to do with MyShake. And so I'm going to tell you the story of MyShake so far. Hopefully it's just the beginning of MyShake's story, but hopefully it has enough motivations that, as I said at the beginning, there'll be the potential to figure out how you can work with us to make this more of a global undertaking. Okay. So the concept I already explained. The concept is that every single one of the smartphones in everybody's pocket has the potential to record useful earthquake ground shaking data. So what we need to do is to figure out how to harness everybody's smartphone. But once we've done that, once we have an app essentially on everybody's smartphone, that's the challenge, then we have the potential to actually record earthquake shaking on the phones. We can collect that information in a central location, servers in the cloud. And of course, we can also then use that information in real time to provide information back to the user, to the app owner, the person who owns the phone, and that's where the early warning piece comes in. If we want to be able to use people's phones, we need to give them something in exchange. What's the best thing that we can give to people in exchange for them letting us use their phone to collect data? Well, we think that the strongest value proposition to make to people is we're going to give you a warning. So that's where the earthquake early warning piece comes into the project. But as an artifact, if you like, of doing that, as an artifact of recording the earthquakes on people's phones and then collecting it to provide them with warnings, we can also collect the seismic waveform data. And we can use that seismic waveform data to do a whole range of research undertakings. These are just some of the examples of efforts that people have expressed interest in so far. And so this includes block-by-block shaking, microzonation types of maps, the response of buildings to earthquake shaking. How do buildings actually perform compared to how they were supposed to form? We can detect earthquakes around the globe. I'll show you some examples. And then we believe that we can actually use them as arrays. This is kind of right at the edge of our research effort right now. We can use them as arrays to detect very small magnitude earthquakes beneath the urban environment and use that to better understand the seismic hazard. Actually, let me just pause. I'm happy to answer questions at any time. So if people want to put their hand up and ask a question during the course of the talk, I'd be happy to do that. Okay, so that's the idea behind MyShake. So the biggest challenge for MyShake is the fact that, unfortunately, phones are not moving because of earthquakes all the time. Obviously, the vast majority of times that a phone moves is because you just went for coffee or you're on your way to work. And so the greatest challenge for the MyShake project is how do we separate earthquake shaking on a phone from everyday shaking on a phone? Okay? And so that's the technology that we developed first, and that was the technology that kind of allowed us to move forward with the MyShake project. And it's illustrated here. We use a classifier analysis. We use a neural network kind of approach. So this is a machine learning approach applied to a very large data set of motions, accelerations recorded on smartphones, including earthquake shaking and everyday shaking. The way we did this, we had an earthquake data set, and then we had students carrying smartphones around for days on end, just recording their motion constantly all day for many days to create this non-earthquake data set. And then we developed this classifier analysis that separates earthquakes from non-earthquakes on the phone. And this is using 2-second windows of data, and we use 3 characteristics. And when we apply that neural network-based approach, we have a 93% success rate, which is really quite remarkable. We went back and did this multiple times to make sure we weren't missing something. But 93% of the time, on one single phone, we can separate earthquake shaking from non-earthquake shaking. Okay? And so that's the really key piece, is by distributing that characterization, being able to, with a relatively high degree of certainty, know that it's an earthquake on a single phone. We can then have the phone contact the back-end servers, and we can then start to do something more interesting with that data. So that's the idea. But that's the key piece, is it's a single phone with a high probability that it's an earthquake, and then connecting to the back end. And of course, if it really is an earthquake, everybody's phone will trigger at the same time. And that's how you confirm that there really is an earthquake underway. Okay, so that's the concept behind MyShake. This just illustrates it by applying it to that algorithm to some data. This is actually for the Napa earthquake, a magnitude 6 earthquake just north of San Francisco a few years ago. And so here's a seismogram, 60 seconds worth of data, and then this is the classifier. It's saying it's not an earthquake, not an earthquake, not an earthquake, not an earthquake, 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 not an earthquake. Okay? So that just gives you a simple example of how on the phone you can determine that it's an earthquake or not an earthquake. And then the counter to that is here is a chunk of 5 minutes worth of data. That I didn't say that at the beginning. So when the phone decides to record data, it records 5 minutes of data. So it has a 1-minute buffer at the beginning. So whenever it thinks that there's an earthquake, it has 1 minute of data pre-earthquake, and then it collects 4 more minutes of data. So you have a 5-minute waveform, the first minute of which is the minute before there was any kind of trigger. And so this is an example of that, and this is a phone that triggered. Okay, not due to an earthquake, just because the phone was stationary and somebody started moving around. And this is applying the classifier to that 5-minute chunk of data. And you can see that it doesn't think it's an earthquake, but for just these 2 or maybe 2 points, it thought it was an earthquake. So it's not perfect, obviously. But that just shows you how the classifier on the phone, again, this is on a single phone. Okay, so that was all done back in 2015. And so in 2016, we launched what was the first public version of the MyShake app. And so you're seeing a video of that public version. This version, or an updated version of this, is still available in the Google Play Store. So if you have an Android phone, you should put this version of MyShake on your phone. And so the first version, again, it was launched in February 2015. And it was really a citizen science undertaking. Okay? So by downloading the app, there's some information about earthquakes. There's a little bit of earthquake education. You can learn about past earthquakes in your region. There's some information about earthquake preparedness. You can see maps of earthquakes. There are many apps that show maps of earthquakes. But then the real push was that by putting this app on your phone, you're going to help us collect data so that we can work towards a public earthquake early warning system. And so that is what we have been doing. We launched this on one Friday in February of 2016, and the project was an immediate success. I can tell you we were sort of hoping at that time when we launched the app had been on 75 phones. Okay? And so we thought it was ready for a little bit of a public test. We were hoping to get to 1,000 phones. That was the goal, 1,000 phones. We decided to try and be prudent, so we planned for about 10,000 phones. We launched it on Friday afternoon, by 6 p.m. Friday, it is on 60,000 phones, and it was already a global seismic network. So immediately, literally in a matter of hours, it became a global network on all but one continent. So far to date, it's been downloaded by over 300,000 users. That's over the course of the last 2.5 years or so. I guess it's almost 3 years now. And you can see it's a global network. There's some interesting gaps. China is a pretty big gap, which is interesting because obviously there's a significant population there. And that's for the simple reason that they don't allow Google. And so there's no mechanism to put it onto phones in China because Google's not in China. But with that one exception, the app is pretty much wherever there are people. Because wherever there are people, there are Android phones and there's a Google Play Store. So the number of users today is 16,000 users. So over the course of the last week, about 16,000 phones have provided data to the network. Obviously, it's still available. You can download it for free. So that's the status of the MyShake today. It's a global network. It's collecting data from earthquakes around the world, and we can start to, and we have been exploring over the last 2 years what we can use with that data, and that's what I'm going to tell you about. I added one extra. I did this morning just to show you. This is this morning. So this is the number of phones that talked to our back end this morning between when I got up and when I came here. And so you can see that I wouldn't say it's a dense network across Europe, but considering that we put this out 3 years ago and have really done nothing with this since, the fact that there are still this many phones across Europe that are recording earthquakes, I think is quite surprising. Okay, but before I go any further, I would just want to introduce the team that is working on this. This is a pretty large effort at Berkeley right now. Chin-Kai Kong, he's now a researcher. He's the person that did the neural network analysis. He's really led the development of MyShake all along. We have a team of 2 postdocs, 2 graduate students and 1 postdoc who are working on the research side of things. We have 2 folks who are focused on the users, a user design. I never thought at a seismology lab we would hire a user experience, sorry, I don't even know the correct term, a user experience designer. But we did, Kaylin and Jen Strauss, and then we have 3 developers so these are the people who are actually doing the work. I just talk about the work. Okay, so let me give you a sense of what the system is doing. So this is the Berkeley earthquake that occurred at the beginning of last year. It's a very small earthquake. It's only a magnitude 4 earthquake. When we released the app, we didn't think we would detect anything smaller than a magnitude 5 earthquake. Okay? So this is a magnitude 4 earthquake that happened at the beginning of last year. It was during the middle of the night. And at the time that this earthquake occurred, all of these sort of greeny blue dots, those were all of the phones that had MyShake on them that were active. Okay, so again, at this point, it was 2 years after we launched the app, and still there are this many phones that are running MyShake. I keep emphasizing this because I never imagined that there would be this many people with enough interest to have an app running on their phone that really doesn't do anything for them. All it does is it collects data from earthquakes. So when the earthquake occurred, the phones that turn orange, those are the phones that are detecting the earthquake on their own. Right, the single phones that triggered on the earthquake and recognized that it was an earthquake. And again, this is only a magnitude 4.4 earthquake. Here's another example from Christchurch. Again, it's only a small earthquake, a magnitude 4.3 earthquake. Again, the sort of greenish dots are the phones that were running MyShake at the time, and you can see that the majority of them actually triggered on this earthquake. So the algorithm that we have that is triggering and recognizing that it's an earthquake underway on the phone is working pretty well. But this is by far the best example, as in the earthquake for which there were most phones. And this is a magnitude 5 earthquake in Southern California, the Borrego Springs earthquake. When you look at a map of Southern California, the earthquake epicenter is pretty much in the least populated part of Southern California, of course. You can see the population of California. The density of MyShake dots really just represents the population of Southern California. And you can see that many phones across Southern California triggered on this particular earthquake. Okay? So the concept of putting an app on private individuals' phones and having that app trigger on earthquakes. I think we've shown that that's possible, that's feasible. Okay? The question now becomes, what can we use that data for, and how can we expand the number of people that are running the app so we just collect more data. Just to give you a sense of the data, this is by a group of seismologists. This is a record section from that same Borrego Springs earthquake. Again, this is only a magnitude 5 earthquake. The green line is the predicted P wave arrival. The red line is the predicted S wave arrival. And this is going out to a distance of about 200 kilometers. And you can see even this seismogram that's furthest from on this plot, that's furthest from the event, you can see the P wave arrival for a magnitude 5 earthquake that's essentially 200 kilometers from the epicenter. So this is much, the sensitivity, our ability to detect seismic phases, both P waves and S waves, is actually much better than we expected. Actually, I'm going to go back because I forgot to point that out. On this animation, is it going to play? How do I make it play? Sorry. Okay, on this animation, the yellow is the P wave, and the second yellow, the darker yellow, is the S wave. You can see the P wave is triggering the phones in Palm Springs. That's important that we can actually detect P wave arrivals. It means that we have a complete waveform. We have the P wave and the S wave. It's also important for earthquake early warning. By detecting the P wave, we can provide warnings before the S wave arrives. Okay, so it's important that we're detecting both the P and the S wave. To give you a sense of what the data looks like, people, for good reason, are very skeptical about the quality of seismic waveform data from smartphones. And so here's a comparison between a MyShake smartphone seismogram and a traditional seismic station that were 1 kilometer apart. So they're not in exactly the same location, so of course we don't expect the waveform to be exactly the same. But you can see, particularly on this version, this is the filtered version, you can see that the two waveforms match each other very well. So this data is data that can be used for many of the kinds of analyses that we use traditional seismic data for. The quality of the waveforms is good enough for those kinds of studies. Okay, and so the network's out there, the network's running, it's detecting earthquakes in an automatic way, and so far we've recorded 900 earthquakes. These are, and our definition here is earthquakes for which we have at least one waveform that is useful for seismic research, as in when you look at it, it looks like an earthquake waveform. Okay, so this is not just phones triggering at the same time as earthquakes. This is seismograms on which you can see P and S wave arrivals. You can see the smallest earthquake we've detected is actually a magnitude 1.6 earthquake. That was a quarry blast in the South Bay, San Francisco. Magnitude 1.6 earthquake that we recorded, and the largest was the Ecuador earthquake, a magnitude 7.8. We've observed earthquakes down to depths of 350 kilometers in the Japan region, and of course all the way up to the surface. So what does the detection capability look like? This is just a simple plot of the magnitude of earthquakes and then the epicentral distance at which we've been able to record those waveforms. And so I've just written up here approximately what this equals. So magnitude 3, we can record out to about 50 kilometers, and magnitude 5 out to about 250 kilometers. But so that's important when we think about how we can use this data. So first of all, obviously there are only phones where there are people. So we're not going to have some global, evenly distributed network like the GSN, just much more dense. Okay, we're going to have very dense networks in the urban environment. And so that obviously focuses the kinds of things that we can use these data for. But we can use this as a regional seismic network. And so this is sort of, I find this less exciting, frankly. We have regional seismic networks. But the point is, if we can use MyShake as a regional seismic network, we then potentially have a regional seismic network in everywhere where there are people and there are earthquakes around the globe. And so to illustrate that, I'm going to just show you from earthquakes in California. So this is that same Berkeley earthquake I showed you at the beginning. This is a magnitude 4.4 earthquake. But now we're applying sort of traditional regional seismic network type processing. So we want to detect the earthquake, we want to locate the earthquake, we want to estimate the magnitude of the earthquake. And so we estimate a magnitude of 4.7 compared to the traditional network magnitude of 4.4, and then the location and the time error are pretty small. And this is just comparing how accurately we can match the traditional network, and we get locations within a few kilometers, and we get a magnitude estimate that's off by 0.2, 0.3 magnitude units, which is typical for what you would expect from one regional network to another. So again, this could provide the capability to develop a global seismicity catalog in the same way we do for individual regional seismic networks. We can also use it to generate shake maps. So this idea of understanding the microzonation of seismic shaking in a very detailed way across the urban environment. This is the shake map generated from my shake data for that Borrego Springs earthquake that I showed you a few moments ago. Now this is the shake map generated by the traditional seismic network. Okay? And you can see that there's a significant difference. You can see that the intensities, the warmer color intensities in the MyShake data are greater than in the traditional seismic network. So there's clearly a systematic difference between the intensities observed on the phones and the intensities observed in the traditional seismic stations. So why is that? Well, here's the same data. So the blue dots are the peak ground acceleration as a function of distance on the phones compared to the red dots, which is the peak acceleration on the traditional seismic sensors. You can see that the spread is about the same. The difference is that the average for the blue is all a little bit higher than the average for the red, and it's about a factor of 1.6 greater. So on average, a MyShake peak ground acceleration is 1.6 higher than a traditional seismic station. Turns out that's exactly what you expect if you're measuring the ground shaking in buildings. All buildings have stronger shaking peak accelerations than the free surface. Of course, when we put out traditional seismic stations, we put them on free surface sites. If you put your accelerometer in a building, on average, the shaking will be a factor of 1.6 higher. So you can look at this as an advantage or a disadvantage. Okay, a traditional seismologist would say, oh, that's terrible. We need to know the true ground motion, the free surface ground motion. That's why we put our traditional seismic sensors at free surface sites. However, a civil engineer would say, wow, this is fantastic. Now we can actually see what the ground shaking in buildings are, and is it what we expect? So if you put those two things together, when we do shake map, okay, when we think about shake map, already shake map has to account for the near surface conditions, whether you're in a sedimentary basin, the VS30 type correction. And so what we're now doing with MyShake is we're just seeing MyShake as having an additional layer. We have the bedrock surface, which is what's used as the basis for shake map. You add on a layer of sediments, and now we're just adding on a layer of buildings. Okay? So once you start to understand the effect of the buildings, you can correct for it to get to the ground motion. But in the process of doing that, we can actually start to understand how the buildings are responding to earthquakes and whether the buildings are behaving as engineers designed them to. And so this is what we've now started to explore with our structural engineer colleagues, is how we can actually extract the characteristics of the buildings from the MyShake data in addition to the characteristics of the earthquake. And so it opens up this possibility of actually monitoring the structural health of cities in addition to the things that we are used to doing with shake map types of information. Okay, so that's my summary of MyShake so far. Okay, we put out this network, we've collected data from these earthquakes around the world, and we've started to explore how we can use it. As I've probably emphasized multiple times already, I'm absolutely shocked that so many people have MyShake on their phone. When we launched the app, we thought that there would be interest, people would download it, and a lot of people did download it. The fact that so many people are still running it 3 years later, I think is testament to the fact that people really want to engage in these citizen science type projects. I would never have guessed that. But that's why people have the app on their phone today. So there's a surprising number of people out there who really want to engage in this scientific endeavor and want to contribute and participate. And I think that's the main reason that a lot of people have the app on their phone. And hopefully what I've also shown you is that the data has value. The data we can collect from MyShake has value, both in terms of scientific study and in terms of reducing hazards. But if this is going to work, it needs to be bigger, and it needs to be much bigger, by orders of magnitude bigger. So that is our goal now, is how do we get MyShake onto many orders of magnitude more smartphones to collect more data. So if we want to do that, we have to talk to the users. We have to understand what users want and what's really going to motivate users to put the app on their phone. And the answers are pretty clear. One of the first order things that people want is they want to get alerts before earthquakes. The whole concept of getting earthquake early warning is something that people get very excited about. They're very enthusiastic about it. It means that they feel like they can take some control over what happens to them in earthquakes, because now they will get a few seconds to a few tens of seconds warning. But in addition to that, what we've also learned is people really do want post-earthquake information. Immediately after an earthquake, they want to know what the distribution of damage is. As they start to kind of recover, they want to know what's going on around them. And then the other piece that is absolutely critical that everybody knows is if you're putting an app on somebody's phone, you must use no power from their phone. The number one way that you will kill an app on anybody's phone is by sucking up their battery life. Because I can tell you, earthquakes are never going to be more important than being able to read their email, check Twitter, call somebody when they want to. So whatever we do, we have to design an app that uses absolute minimal power, otherwise it will go nowhere. This is something that I emphasize because most people in the seismology community, myself included, think, well, of course people will want to use their battery power to detect earthquakes. But guess what? That's not people's first priority. That's not why they buy phones. Okay, so we want to do earthquake early warning. So I think most people in this room probably know what earthquake early warning is, but I just want to show one very simple video clip that illustrates why earthquake early warning is useful. So that siren, this is from Mexico City. That siren you can hear in the background is the early warning system in Mexico City, and these people are in the street because they heard the earthquake early warning. So the idea behind early warning is you provide a few seconds, a few tens of seconds warning so people can get out of hazardous situations. And I don't think I need to make the argument as to why that can be useful for people. In this case, in the case of Mexico City, of course, there's a concern about a lot of these unreinforced concrete buildings. That's why they built the early warning system with a public loudspeaker system so that everybody across Mexico City can hear the alerts. And the system is very popular, needless to say, in Mexico City. And so the idea behind MyShake is that we can basically do, or we would like to be able to do, earthquake early warning wherever there are phones. And guess what? Pretty much wherever there are people, there are now smartphones. So this opens up the possibility, if we can do early warning using the MyShake earthquake detection capability, we could do earthquake early warning around the globe. And so that's what we're now working towards as rapidly as possible. So the only piece that I haven't shown you that we need for this technology to do early warning is the alerting piece. Okay? So this is the Borrego Springs earthquake. You've already seen the detection. So all of these phones that are detecting, those are real detections in the earthquake. Since that time, we've developed the algorithm with the experience we've gained of how MyShake phones detect earthquakes. We've developed an algorithm to take all of those individual phone detections and turn it into an event detection. So we need to locate the event, we need to estimate the magnitude of the event, and then we could potentially push out a warning to the people that are going to feel the earthquake. And so that's what you're seeing an animation of right here. It's obviously going to run a couple of times. The algorithm has a threshold at which it issues the warning, and the point at which it issues the warning is when you'll see this red box appear in the animation when it runs again. The initial estimate of the magnitude is 5. This was actually a magnitude 5.2 earthquake. What we're doing is oh, here we go. So let's let it run. So this again is the P wave and then the S wave. When the P wave hits Palm Springs, and now is when you push out the first warning. So the warning is actually issued before the S wave. This is the S wave, before the S wave reached Palm Springs. Of course, the alert takes a few seconds to come out because we have to wait for the P wave arrivals to get to a populated region, Palm Springs. But once a significant number of phones in Palm Springs have seen the P wave arrival, the earthquake is detected, the magnitude is estimated, and we push out the warning. And the current concept is that we would issue a warning to the region where the shaking intensity is going to be 4 or higher. Shaking intensity 4 is a little lower than light shaking. Shaking intensity 5 means light damage. So intensity 4 is lower. Intensity 4 means many people feel the earthquake inside and outside. So we're not going all the way down to felt shaking, but intensity 4. And so the red circle is the region where you expect intensity 4 to occur based on it being a magnitude 5 earthquake. And so of course it encompasses a much larger region than the Palm Springs region, which is where we detect the P wave in order to generate the alert. Okay, so that's how, so this is real MyShake triggers, because the phone's triggered, those are real triggers, but then with the alerting algorithm placed on top. But to show how this would work in other regions around the world, of course, we can't wait to have all of the necessary data. So we've created a simulation platform which we have done our best to represent how MyShake will operate based on all the observations we have from MyShake around the world, okay? And I'm not going to go into how the simulation platform works, but things that we've taken into account is that, of course, only a fraction of the population will ever put MyShake on their phone. We can't expect 100% of people to put MyShake on their phone, so we're going to assume that 0.1% of the population put the MyShake app on their phone. And we think that's reasonable because it turns out that 0.1% of the population of Los Angeles has put MyShake on their phone. So that's a reasonable estimate. We use ground motion prediction equations to estimate the P wave and the S wave amplitudes, and we use those compared with observations of what triggers MyShake phones to build a probabilistic model that any individual phone then triggers based on the amplitudes. We have an empirically derived statistical model of phone detections. To illustrate that, this is the nighttime detections versus the daytime detections. So the phone obviously can do a much better job of detecting. In fact, it can only detect when the phone is stationary. So in the middle of the night is ideal because most people's phones are on a nightstand or wherever they're stationary. In the daytime, the number of phones that detect an earthquake of a given size drops significantly. So it's 90% in the middle of the night. It drops down to 20% in the middle of the day. And things like this are taken into account in this simulation. And then, of course, we also include uncertainties in the seismological characteristics as well. So we put all of that into the simulations to do our best job of representing how a real MyShake network could perform if 0.1% of the population put it on their phone. So here's some recent earthquakes to show what might be possible. Okay, so first of all, this is the earthquake in Indonesia last year. It killed just over 2,000 people with the earthquake and then the tsunami, of course, that came in into Palpo here. And so I'll just run the animation again. Again, the dots are the MyShake phones, so 0.1% of the population. And then these are the ones that are triggering based on the characteristics that I just talked about. And so this one, the initial warning was a magnitude 6.6 earthquake. And so the region that would be warned, you can just see the corners here. So this whole region essentially would have gotten an alert because the system would have estimated shaking intensity 4 for the entire region. And the time at which that alert goes out in this simulation for Palpu, of course, which is where there was a lot of fatalities, mostly due to the tsunami, just to be clear. But there would be a warning time of 13 seconds. Okay, so that's a significant warning time. Of course, this also emphasizes the need that this has to go along with education. It's great for people to get alerts, but they need to know what to do with these alerts, both given the earthquake and the tsunami potential. Here's another example. This is the Nepal earthquake. This is actually the earthquake that really stimulated us to think about this, because when we tried to get data from traditional seismic stations in the region, it was impossible to get any data at all. And then we realized how many smartphones there are in Kathmandu. There's 600,000 smartphones in Kathmandu. And so here's a simulation for what the warning might look like in a repeat of this earthquake with MyShake on 0.1%. Of the population's phones. Kathmandu in this case would have about 17.5 seconds worth of warning. Okay, and then finally, I'll show an example from closer to home. This is a repeat of the Loma Prieta earthquake, which of course was the last major damaging earthquake for us in the San Francisco Bay Area. And so this earthquake was down here close to Santa Cruz. The alert goes out, the magnitude 6.3. The warning, even for San Jose, is 4 seconds. The warning up for San Francisco and Oakland is up closer to 20 seconds. So again, these are all simulations, but we've spent a lot of time trying to come up with all of the reasons the system won't work and incorporate it into our simulations. So we believe that this really shows that there's a good potential that we could actually deliver warning using this network based entirely on smartphones. And so encouraged by this, we're moving very rapidly now into what we're calling MyShake 2.0. So this is a completely redesigned version of the app that we hope will have a lot more downloads than even the first version did. It's a much more attractive interface, courtesy of our user experience designer, as opposed to being designed by a seismologist. So a much more attractive user interface, new features requested by users. I'm going to show you some of those in a moment. And the entire system has been built on human-centered design. So we've tried to get away from the idea we're building an app for seismologists, and instead we're building an app for people who are concerned about earthquakes. So the plan is to launch this in a couple of months, and to give you a sense of how we're going to launch this and how we're trying to appeal to people to download the app. This is sort of the way that we present it. So get earthquake ready and help your community. Have earthquake information at your fingertips and help create a global earthquake early warning network. Oh, and very importantly, it will be available for both iPhones and for Android. Okay, why is my, oh, there we go. Help develop earthquake early warning systems. Your device becomes an earthquake sensor and joins a smartphone network collecting valuable data. Quickly understand the impact of earthquakes. See damage and shaking reports submitted by other community members, along with information from the USGS and other global earthquake authorities. This is where the partnership piece that I started with starts to come in. Stay informed, get notifications about nearby earthquakes, and track earthquakes around the globe. Of course, we need people to have this on their phone all the time, so it's ready for an earthquake rather than just putting it on their phone after an earthquake. So we have to give people something in between. Share your experience. If you felt an earthquake, share your experience and see what other users are reporting. So that's how we're going to project it to people. The idea is that the app will have the capability to deliver alerts. The alerts will be very straightforward. Drop, cover, and hold on with an audible sound and also a visual. You can see here, drop, cover, and hold on again. So this is obviously a very US-centric approach to delivering the alerts right now. And obviously what we will want to do as we use this in more regions around the world is have the right collaborations with the emergency response community to tailor the message differently for different regions. But this is what it looks like right now. And so obviously what's important is that there has to be an audible message. Oh, it's going to keep going. It has to be an audible message so that your phone is off somewhere and you understand that there's an earthquake because you need to take action before you pick up your phone and start doing anything with it. So that's why the audible message. The nature of the alert message has actually changed significantly. When we first started working on earthquake early warning, we had a demonstration app called MyEW that we used to show that early warning was possible using traditional seismic networks. And it showed, as you can see in this here, it showed a countdown until it was 3, 2, 1. It would count down until the shaking, and it also showed the shaking intensity. We now understand that that's a mistake based on our interactions with the emergency response community, with social scientists, with people using earthquake early warning. A lot of this was learned in the earthquakes in Mexico City a couple of years ago. And so now the message is very simple. The message is simply earthquake, shaking expected, drop cover and hold on. We don't tell people how strong the shaking is going to be. We don't tell people how long until the shaking occurs, because neither of those things mean anything to people. If you tell people what the shaking intensity is going to be, they think you're talking about magnitude. They don't understand the difference between magnitude and intensity, so there's no point in sharing that information. And experience has shown that our best estimates of when the shaking is going to start are usually wrong. So there's no point in giving people a countdown until the shaking starts either. It will have real-time information about earthquakes around the globe, so a map of earthquakes around the globe, recent earthquakes that you can click on and get additional information. And then for earthquakes that have caused damage, when you go in, you'll be able to see the distribution of damage that have been reported by people using the app. This doesn't seem to be working. And so this is how people will report the app. If you feel, there's a button, just like did you feel it in the US for the USGS? If you felt it, you can click on the button. It asks you when you felt it, where you were located. You drop a pin where you were located, and then you can say what the strength of the shaking was, and you can report what the damage was. And that goes to the back end, and then that's shown to all of the users on the app from that point on. And then finally, just to finish up, what we're doing now is we're trying to expand. We built the system with the idea that if we want to do everything on phones, so we want to detect earthquakes on phones and we want to issue warnings to people on phones, because if we can do everything on phones, we can do it everywhere in the world. That was the original objective. Okay? So we're very close to that now, and that's kind of still the objective that we're on, but we also see that there's real value, of course, in incorporating other sources of information into the system. So specifically, in some parts of the world, there are already early warning systems using traditional seismic networks, and we want to be able to use that information to also deliver warnings to people and put the app on people's phones so that we can also collect the data. And that's why we've started talking about the MyShake platform. And what I mean by the MyShake platform is that any early warning system, it's made up of 3 key pieces. There's the earthquake detection piece. There has to be a sensor network, a network of seismometers. There's the decision maker piece that's collecting that information and deciding when to issue an alert. And then there's an alert network where you push the alerts out to people. Okay? And of course, everything I've been talking about up until now is this whole piece is within the MyShake project, right? So the phones detect the earthquake, MyShake decides when to send out an alert, and the alert goes back out to the phones. But there's no reason why we can't take data from other seismic networks, from traditional seismic networks. There's no reason why we can't take alerts that have been generated by other networks and push them out to phones as well. And so that's what we're starting to explore doing. And we're going to start by doing it back in our home territory, back in the US. Actually, but before I talk about that, this is just a map that shows my understanding of the current status of earthquake early warning around the world. So there are a few places in the world where alerts go out to the public: Mexico, Japan, Korea. There's some representatives from Korea here today, and Taiwan. And there are alerts being generated in these 4 places that are broadly distributed to the public. There are other places where alerts are going out to selected users. That includes the United States, Romania, Turkey, and India. And then there's a pretty long list now, and I'm sure this is not complete. There's a pretty long list of places where people are exploring doing earthquake early warning. And so the idea here with the MyShake platform is if we built this capability to push out the alerts to smartphones, well, we can help any of these groups distribute the alerts by plugging their alert system into MyShake, and then MyShake can distribute the alerts. And what's actually driving this is in the United States, we have an early warning system that is generating alerts for the entire west coast of the United States. The USGS has said, yes, this is ready to provide public alerts, but almost nobody is getting alerts because there's no technology to deliver the alerts out to people. Okay, there are exceptions, which I'm happy to talk about. The point is that the vast majority of people in the US are not getting access to shake alerts, to the alerts that the system is generating. And so MyShake is actually going to be used to start delivering Shake alerts to everybody in the US. As I just said, Shake Alert is technically a public system. Public alerts were rolled out in October of last year, but very few people are getting the alerts. And so we're actually now going to start using MyShake 2.0 to deliver Shake alerts to anybody who wants them in the west coast of the United States. So that's the goal, is that we roll out Shake Alert 2.0. In some regions, we can immediately start delivering alerts if they're being generated in the western US. And then we want to start delivering alerts in other regions where we have enough density of the smartphones to be able to detect the earthquakes and generate the alerts. Okay, so to summarize my last slide, what we're trying to do here is we're trying to build synergies amongst many different areas of interest in seismology and earthquake hazard reduction. So what's been driving all of this, really, frankly, is scientific discovery, and the scientific discovery leading to hazard reduction. The hazard reduction leading to user application. There's no point in a group of academics coming up with mechanisms to reduce hazard if it's not applied, okay? So hazard reduction leading to user applications. User applications, I think, can lead to this citizen science, and we're hoping to close the circle and have the citizen science lead back to scientific discovery. And so obviously what I'm talking about, the hazard reduction is earthquake early warning that has this user application. I think as we get user application of earthquake early warning, the impacts for hazard reduction are actually much broader. By people having early warning on their phones, I think they become more aware of earthquakes, the earthquake risks, and so there's an education and a preparedness piece. By engaging society as a whole in this concern, getting them to put MyShake on their phones, we can actually start to collect more data, and that will lead to further scientific discovery in the domains that I kind of touched on at the beginning. So that's our hope. We will see. Okay, well, I thank you for your attention. I'll stop, and if anybody has questions, I'm happy to answer them.